Lecture 8.1, Sequences. The photo is of one of the more green and lush areas of Craters of the Moon National Park in the state of Idaho. A sequence is a list of numbers written in an explicit order. We can designate each number as a sub 1, a sub 2, a sub 3, etc., where a sub n would be the nth term. Any real-valued function with domain a subset of the positive integers is a sequence. If the domain is finite, then the sequence is a finite sequence. In calculus, we will mostly be concerned with infinite sequences. A sequence is defined explicitly if there is a formula that allows you to find individual terms independently. Example, a sub n equals -1 to the n over n squared plus 1. To find the 100th term, plug in 100 for n. A sub 100 equals -1 to the 100th power divided by 100 squared plus 1, or 1 over 10,001. A sequence is defined recursively if there is a formula that relates a sub n to previous terms. For example, given b sub 1 is 4, and b sub n equals b sub n minus 1 plus 2 for all n greater than or equal to 2, we find each term by looking at the term or terms before it. If b1 equals 4, b2 would be b1 plus 2, or 6. b3 is equal to b2 plus 2, or 8. b4 is b3 plus 2, or 10. You have to keep going this way until you get to the term you need. An arithmetic sequence has a common difference between terms. For example, the sequence -5, -2, 1, 4, 7 has a common difference of 3. Because 3 is the number you would have to add to each term to get the next term. The sequence ln2, ln6, ln18, ln54 is not as obviously an arithmetic sequence, but it does have a common difference. If we take ln6 minus ln2, that can be rewritten as ln6 over 2, or ln3, and we find that same common difference between each succeeding term. Arithmetic sequences can be defined recursively. A sub n equals a sub n minus 1 plus d, where d is the common difference, or explicitly. A sub n equals a sub 1 plus d times n minus 1. Where n minus 1 is the number of times you have to add the difference. For example, if you wanted the 10th term, you'd have to add the difference 10 minus 1, or 9 times. A geometric sequence has a common ratio between terms. For example, 1, -2, 4, -8, 16. To get the next term, we're multiplying by -2 each time, so r equals -2. 10 to the -2, 10 to the -10, 1, 10. The common ratio is 10 to the -1 divided by 10 to the -2, or 10. 10 is the ratio that we multiply each term by to get the next one. Geometric sequences can be defined recursively. A sub n equals a sub n minus 1 times r, or explicitly. A sub n equals a sub 1 times r to the n minus 1. So n minus 1 is the number of times you have to multiply by r to get the desired term. For example, if we want the 10th term, we'd have to multiply by r 10 minus 1 or 9 times. So we have a sub 1 times r to the 9th. Example, if the second term of a geometric sequence is 6 and the fifth term is negative 48, find an explicit rule for the nth term. We have a sub 1 times r to the 4th is negative 48 to get the fifth term. If we put that in the numerator, and a sub 1 times r equals 6, which is the second term, in the denominator, we can cross out a sub 1 and get r cubed equals negative 8. So r must equal negative 2. Now that we know the common ratio, r is negative 2, we can write a sub 2 equals a sub 1 times r to the 2 minus 1, or 6 equals a sub 1 times negative 2. So negative 3 equals a sub 1. Our explicit rule for the nth term then is a sub n equals negative 3 times negative 2 to the n minus 1. Sequence graphing on the TI-nspire. Example, plot a sub n equals negative 1 to the n times n minus 1 over n. Press Menu, 3, Graph Entry Edit, 6, Sequence, 1, Sequence. Enter the expression. Leave the initial terms blank for explicitly defined functions. We'll graph the first 20 terms. Press Enter. There's our sequence. Use Zoom to change the viewing window so that x is between 0 and 20. We see that the sequence alternates back and forth and doesn't converge to a single value. The previous example was explicitly defined. Now we will use a recursive definition to plot the Fibonacci sequence. We have a sub 1 equals 1, a sub 2 equals 1, and a sub n equals a sub n minus 2 plus a sub n minus 1. We have the first two terms, and you may remember that to generate the Fibonacci sequence, to get each term we add the previous two terms. After clearing the previous graph, press Menu, 3, Graph Entry Edit, 6, Sequence, 1, Sequence. We enter the expression as u1 n minus 2 plus u1 n minus 1. In this case, the u1 with the parentheses n minus 2 is not multiplication and is not really a function. This is the way the calculator represents a sub n minus 2 and a sub n minus 1. We send our initial values as 1, 1. Enter the initial values separated by a comma. Graph the first 20 terms. then press Enter. There are our first terms in the Fibonacci sequence. We use zoom to change the viewing window to 010 times 040. You can use trace to investigate the values. Notice that the initial points are in green. We can also look at the results in a table. Press Menu, 7, Table, Enter. And we get our table. Notice the 0 term is not defined. Scroll down to see more values. When you are done with the table, press Menu, 2, Table, 1, Remove Table. You can determine if a sequence converges by finding the limit as n approaches infinity. Example, does a sub n equals 2n minus 1 over n converge? I take the limit as n goes to infinity of 2n minus 1 over n, which we could separate as the limit as n goes to infinity of 2n over n minus 1 over n, and separate into two limits, the limit as n goes to infinity as 2n over n minus the limit as n goes to infinity of 1 over n. In the first limit, the n cancels out, and in the second limit, as n goes to infinity, we get 0. So we have 2 minus 0, or 2. The sequence converges, and its limit is 2. Note that we could have also approached this problem with a shortcut if we consider dominant terms. As n goes to infinity, the negative 1 becomes insignificant, and we get 2n over n, which is 2. The absolute value theorem for sequences. If the absolute values of the terms of a sequence converge to 0, then the sequence converges to 0. Don't forget to change back to function mode when you are done plotting sequences.